Hello, this is your famous YouTuber here again with another Anarculus production. Dun, 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 dun. Of course, all the famous production companies in America and around the world have a theme song. So, why wouldn't Anarculus production dun, 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 also should have a theme song, which it now does. Of course, just because I have over 60 views on more than one of my videos does not make me famous. But I am certainly on the way, and people are beginning to notice. As a result, as you can see over here in the bottom right-hand corner, I've added a new layer of security to my watermark so that people cannot illegally pirate my movies like some of the other more famous directors. Because remember here, I am the director, the producer, the star, and the editor of all of these Anarculus productions. Dun 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 dun! Alright, so let's get this show on the road here. Today we're going to talk about the calculus of other bases that we haven't yet discussed. These are kind of general formulas here. So we're going to start with y equals a to the x, where a is greater than 0 and a is not 1. So we're talking about excuse me, functions like 2 to the x or 5 to the x or 1/2 to the x. How would you derive those? Alright, so let's do it. We can do this. We can provide a proof for this pretty easy. If we start with y equals a to the x, the problem is we can't actually derive this. We don't have a rule for it, so we're going to have to do something to help us out. We're going to have to get this power down out of here. Well, to get the power down, we did this in the last section. We take the natural log on both sides. That allows us to take the power and put it in the front. So that'll give us ln y equals x times ln a. Now remember, a is a number, so this is a number here like ln 2. Okay? So this is now implicit. The derivative of ln y is 1 over y, but you derive the y, you need the dy dx. The derivative of x ln a. Remember, this is a number times x, so it's like a 5 times x. Its derivative would be ln a. Okay, derivative of x is a 1, and just leave the ln a there. Multiply both sides by y, and dy dx is equal to ln a times y, but y is a to the x. So the derivative must be ln a times a to the x. And that is the rule. So we're going to put it up here in just a second here. So our first rule is the derivative of a to the x is ln a times a to the x times, use the chain rule on the exponent. Alright? That's going to be our first rule. Okay? And we just proved it down here. As I erase it, we already proved it. Okay. Now, I have a couple of things to say about this. Well, what I'm more interested in is what we talked about in the last section, which was the derivative of e to the x. Okay? We know that the derivative of e to the x is e to the x times the derivative of the exponent up here, right? That's the chain rule part of it. But e is a number. E is like 2.718. So this rule should be very similar to this rule. These two rules really should be the same. So I guess my question to you is, why aren't these rules exactly the same? Okay, why aren't these rules exactly the same? They certainly look similar, but they're not exactly the same. Why aren't they exactly the same? Alright, that takes care of our first rule. Okay, alright, so let's do a problem here just to say we did it. Let's let y equal x times 6 to the negative 2x. Okay? This is a product rule problem. So dy dx, the derivative, leave the x there. The derivative of 6 to the negative 2x is ln 6 times 6 to the negative 2x times the derivative of the exponent here, which will be a negative 2. And that's the chain rule part, plus leave the 6 to the negative 2x, the derivative of x is 1. Okay, take out your 6 to the negative 2x, it's in common in both. And you have negative 2x ln 6 plus 1. And that's the right answer. Okay? It's just an application of a simple rule. All right? Okay? Nothing too complicated. All right? So there's our first example of our first rule here. Okay, let's get rid of this. And we'll get rid of this. And next we're going to talk about, well, so far we know how to derive the natural log of x. Right? So I want to derive a log with any base. How do I derive a log with any base with x as its argument? Well, to do that, we're going to have to rewrite y equal log of x with base a. Okay. And then we can switch this around to exponential because I don't know how to do anything with this. So I could write x equals a to the y. And now I'd really like to derive this. Okay? But the question is, how do you derive this? Well, that's the question that I'm going to leave up to you to derive. I'd like you to derive this, but I will tell you the final result. The final result you should get is 1 over ln a times x times the derivative of the argument of the log. This is the chain rule part. This won't show up in your answer when you actually go and derive this. Okay? Figure out how to derive this. And again, here's a hint for you. You got to get this power down. And then you can do implicit. And off you go. Alright? So think about that. But that's the rule that you're going to get. Okay? Alright, so let's go ahead and try that one just to say we did that one. Let's say h of x is equal to log base, let's not even put a base, of x squared plus 1 over x. Okay? There's two ways you can do this. You can do this straight out, just like this, or you can pull it apart because the log properties do apply. It's up to you, whatever you want to do. I'm going to pull it apart and write log of x squared plus 1 minus log of x. And I'm going to go ahead and derive this. So to derive it, the derivative of log of x squared plus 1 is 1 over, now it's the natural log of the base. Well, there is no base there, so it's understood to be base 10. Okay, so we have 1 over ln 10 times x squared plus 1 times, in the numerator, the derivative of the argument of the log. So we're going to have to derive x squared plus 1. We'll leave it for the next step. Minus log of x, its derivative is 1 over ln 10 times x times the derivative of x, which is not going to make any contribution, right? It's going to be a 1. So the derivative of x squared plus 1 is a 2x. So we have 2x over ln 10 x squared plus 1 minus 1 over ln 10 times x. Okay? We need a common denominator now to clean this up. The common denominator is x, or it's ln 10, which already appears in both. ln 10 x squared plus 1 times x. So this first term needs an x, the second term needs an x squared plus 1. So we have 2x squared, that first term needed an x, minus quantity x squared plus 1. And that will be x squared minus 1 over ln 10 x squared plus 1 times x. And you could factor this if you want, but it's not in the guidelines, and there's no reason to because nothing cancels here. So this is going to be your final answer. You're done with this. Okay? So that one's done. And again, let's go back to what we talked about earlier. So back in 5.1, we said the derivative of ln x. Let's get rid of this for a second. All right, so just a simple derivative. So back in 5.1, we said the derivative of the natural log of x is 1 over x times the derivative of the argument of the log, which is very similar to this, right? However, this is missing something. Can you tell me why it's missing what's up here? Okay, can you tell me why this is missing the extra piece that's up there? All right, that's my question to you. Okay? Next, let's talk about how you would derive this. How would I derive x to the x? Okay, x to the x. Well, we have rules floating around for a couple of things in terms of powers. We know how to derive x to the n, right? It's nx to the n minus 1 times the derivative of x. That's the power rule, yeah, like x squared. Okay? We now also know how to derive a to the x. So that would be 2 to the x. So that would be ln2 or ln a times a to the x times the derivative of the exponent. Okay, we know how to derive this, we know how to derive that. So we know how to derive things like x squared, we know how to derive 2 to the x, but there is no rule, there is no calculus rule at all for deriving a variable to that same variable power. So if you want to derive a variable to the same variable power, you have to get this variable power down. So you're going to have to take the natural log on both sides. Okay? That is something that you have to know, you have to be aware of. So this is going to be ln y equals x times ln x. Now this is implicit, you're going to have to derive it implicitly. The derivative of ln y is 1 over y times dy dx. The derivative of x ln x is a product rule problem. Leave the x. The derivative of ln x is 1 over x times the derivative of the argument of the log, but it's not going to do anything, so it's times a 1, plus leave the ln x. The derivative of x is 1. So that gives me 1 over y dy dx is equal to 1 plus ln x. We can multiply both sides by y to try to solve for dy dx. So dy dx is equal to 1 plus ln x times y, but y is x to the x. So this is 1 plus ln x times x to the x power. And that's the correct answer. This is the correct answer here. All right. Not too difficult, not too complicated, but again, it's something that you have to be able to recognize. All right, it's something that you have to be able to recognize. Okay? Finally, our last rule here for the first half of Chapter 5 is how you would integrate a to the x dx. Okay, well, we know how to derive it. The derivative of a to the x is just ln a times a to the x. Right? So to integrate a to the x dx, you should recognize that it's pretty similar. Okay? It certainly involves an a to the x. Okay? It's integral. However, rather than being ln a times a to the x, it's 1 over ln a times a to the x. Which should make sense because you would need this 1 over ln a to cancel this ln a that's here to get back to where you started, right? If you derived this, remember you should get that. Right? And you need a plus c on there. All right? All right, so let's talk about another example here. We have, let's try the integral of 2 to the sine x times cosine x dx. Okay, so what do we have? Well, I'm asking you to integrate that. That certainly doesn't look like that, right? It's 2 to a variable power, so I guess I'm going to try to use substitution on it. There's nothing else for me to do. I'm going to try to let u be sine x. Its derivative is cosine x dx, which is conveniently sitting there. That's good. That's going to go for the du. So this is going to be then the integral of 2 to the u du. And the integral of 2 to the u is 1 over ln 2 times 2 to the u plus c. But u is sine x. So that's 1 over ln 2 times 2 to the sine x plus c. And that's the correct answer. Okay, nothing more to it than that. All right? So far, so good? Okay. Oh, wait. Hold on 1 second. Hello? Yes, this is he. Yeah, I might be interested. Listen, have your people call my people later. I'm in the middle of something right now. I'm making another math video here for the YouTube. Obviously I've found some major fame here working on YouTube, so you're just going to have to call my people, and then maybe they can talk to your people. Call my people. All right, and then maybe we might be able to work something out. If I'm available. All right. Goodbye. Sorry, folks. That was some guy, J.J. Abram. Something about some movie, Star Wars, Episode 9 or something they want me to be in. I don't know. Yeah, I've gotten a few opportunities since this hit, the YouTube hit, and well, we'll see. We'll see how it works out. All right, and actually, well, that's it. That's all you really have to know. So, I'd like to thank you for joining me for another Anarculus production. Dun, 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 dun. Thanks for clicking. Good talk.